In this lecture, we're going to discuss flexure and axial interaction in columns. You can find information about this in chapter 11 of your textbook, which I've uploaded to the Blackboard site. So first of all, what is flexure and axial interaction, and why do we care about it? Well, first of all, let's do some simple examples here where we can see their interaction. So consider on the left a cantilever type structure with a vertical load. If you analyze the beam, you'll see that there are just bending moment and shear acting on the beam. But once you start looking at the vertical column, you find that in addition to the vertical load acting on the column, you also have bending. And so this is a case, as an example, where you have combined axial and bending, and you have to design that column to resist both of these effects. Consider on the right simple frame fixed at both ends, subject to a vertical load like a dead load or a live load. Again, when you look at the beam, you'll have mostly shear and bending moment, maybe a small axial force. But when you look at the column, you definitely will see bending moments and also vertical loads due to the gravity load effect. And so you have to design that column to resist both of these effects. But probably more important, it's the case when you have combined vertical and lateral loads, like in the case of an earthquake, where let's say you have this simple frame here, 3 stories, subject to gravity loads, and also subject to a lateral earthquake effect. In this case, if you look at a column, say on the second floor, you're going to find axial loads acting on it, horizontal loads due to the earthquakes, and hence bending moments of the column bending like this due to the earthquake, lateral force, bending moments due to the earthquake, and then the axial load due to the vertical loads. So we have to be able to design these kinds of columns to resist these combined effects of bending and axial. If you look at a particular cross-section, what you find is that when you have axial P and bending M, that can be made equivalent by simple statics, right, to a axial load acting eccentric with respect to the centroid of the cross-section, and we call that the eccentricity, right? And we can simply find it by dividing the moment by the axial load, and we get the eccentricity. Here are some pictures of a laboratory test when you have a column subject to axial load and bending combined, right? And this is an example of a building that failed due to the combined effect of axial and bending. This is in an earthquake induced type of damage, and you can see here clearly that the columns have been displaced by a lateral force, but they are also subject to the vertical load effect from the weight of the building. Here is a more dramatic example. This is a viaduct in Japan that failed due to the combined effect of axial and bending induced by an earthquake, right? You can see here another shot. This is almost unreal. You see the overturning moment basically destroying these giant columns. So the idea to show you these pictures is just to show you that it is very important to design columns not only for their axial loads but also for lateral effects that create bending combined with axial. So in the case of this column here, what you have is a bending moment, shear, and axial. Right? So how do we perform this analysis? So let's start with a simple rectangular column, cross-section, height h, width b, and let's say we have rebar at two extremes of the section, and that this section is subject to a bending moment that creates, let's say, compression on the top and tension in the bottom, just as an example. So basically the procedure to design columns for combined axial and bending is based on something called an interaction diagram. And the way that we generate these diagrams is basically by changing the depth of the neutral axis, and as we change that depth, we compute the resulting nominal axial load and bending moment that result from the neutral axis being at that location. So say in this case we pick a value of C, whatever that may be. From that we set the concrete failure strain at 0.003 specified by ACI, and from there we can compute the strain in the steel, in this top steel here. We compute it by simple triangle similarity, right? And we can compute the strain in the steel at the other extreme also by triangle similarity, right? So this is assuming plane sections remain plane, which is an overall design assumption that we make for reinforced concrete elements. Once we have the strain in the steel and the strain in the concrete all as a function of C, we can go ahead and compute the forces in the section. The forces in the steel are going to be given by the stress-strain relationship in the steel, which I'm showing here in the bottom right. The steel behaves linear until it reaches the yield strain of 0.0021, and then after that it plateaus to the yielding stress. So if we now turn these strains into forces by using constitutive laws, we can find the compressive force in the concrete, the compressive force in the steel, and the tension force in the steel. They're labeled here as CC, right? Is the compression force in the concrete given by the equivalent rectangular block shown in blue. Then we have the compressive force in the steel, which is the strain in the steel times the elastic modulus, or otherwise Fy if the strain has exceeded the yield strain, and the same thing for the strain in steel in tension. When you add up all these forces, you obtain this equation here, which gives you the sum of all forces, which in this case is not going to be 0, it's going to be some value which we're going to call P sub n. We can do the same thing for bending moments. We simply take every force and multiply it times its distance to the centroid of the section, which is the point at which we are referring all the mechanical elements like axial, shear, and bending. And you can see the expression here in the bottom for the sum of moments. It's basically every force times its corresponding distance to the centroid, and that is going to result in a value called m sub n. So as you change c, you get different values for p and m sub